Hello, I'm back. Still having a little bit of iPad issues, so these will be put together, but there'll be a little bit of a break in there. One thing I wanted to talk about before I moved on to adipose tissue physiology is to talk about the Moriano paper. We've talked about the Cross and the Purslow paper, and this is also from the Purslow paper, so hopefully you can get some feel for those things that I've been discussing. I'd like you to bring any questions that you have to class on Tuesday so that we can spend a little bit of time talking about that. I do want to talk about the Moriano paper. I'd like you to get that paper out. I told you that I'd kind of talk about the strengths and weaknesses of papers. I really like this paper, and what I really like about it is I like the discussion. I think it does the really good job of helping you understand where the science was up to the point that this was published. Now, one of the things that I will tell you is a little bit of a negative about the experimental design of this paper is that they only have an N of 6 per subcell. That's not a lot. Normally I wouldn't accept it based on some of the work that they were doing. But they were using this paper to set up a new thought. And so keep that in mind as we read it. So they had 18 genetically similar rams. 6 of them were maintained intact, and if you look at table 1, you can see that they have 6 rams, 6 wethers, which are castrated rams, and then they have 6 wethers that they castrated and then supplemented with zeronol. So the first thing I'm going to look at in this paper is, did these animals end up what I would expect in the literature for rams, wethers, and zeronol implanted wethers? So if you look at the hot carcass weight, well, that was not significantly different. The zeronol and rams were heavier in live weight than the wethers. The wethers were the lowest. In all these scenarios, the rams should be different than the wethers, with the zeronol lambs in between. Zeronol is a testosterone-based implant, and what they were trying to do is to induce some secondary sex characteristics and then see, based on the differences in growth, if there was a difference in collagen and the collagen physiology. So the next thing I looked at was the fat thickness. And in this case, the fat thickness was much higher for the wethers, and the rams and the zeronol treated wethers were very similar, and there was a statistical difference. Now in this study, they pulled out the splenius muscle, and that is a muscle that testosterone influences, and animals that are showing secondary sex characteristics as males usually have more developed splenius muscles. So that's why they pulled it out, and they reported it in grams as percent hot carcass weight and as a percent of shoulder and neck, because shoulder and neck levels should also, or volume of meat should increase in rams versus wethers. And as I look at these data, you notice that for the weight of the splenius muscle, and remember these are similar genetic types, similar frame, everything, so they should be somewhat similar in muscle weight, but the rams had a heavier splenius muscle than the wethers, and the zeronol treated were similar to the rams. So that and in between, but still similar to the rams. So that's what I would expect. The zeronol might be in between, but zeronol animals treated with zeronol usually do show secondary sex characteristics. So they accomplished their goal by doing this. What did they measure? I'm going to accept that this is a good population to test their hypothesis. So they were going to look at collagen and tenderness. So in table 2, and very interesting, only 2 tables, right? Table 2, at the bottom of table 2, they have their treatment set up the same. notice that what I would expect in Warner-Brasler shear force would be that the rams would be toughest, the wethers would be the most tender, and the zero and all treated would be in between. And remember, for shear force, a higher value means that there's higher amount of force required to segment the core. So a higher value is tougher, a lower value is more tender. And if you look at the Warner-Brasler shear force, which were significantly different, you notice that the rams were the toughest, the wethers were the most tender, and the zero and all implanted were in between. Exactly what you would expect based on the literature. So now they measured some collagen components. They did total collagen, soluble collagen, and insoluble collagen, and they reported these as micromoles per milligram. I talked about milligrams per gram, same measurement. So for total amount, assuming that they started out with the same raw weight, and what you notice there is that the soluble collagen is higher, in the rams and the zero and all treated than in the wethers. And if you go down to percent soluble, which is the normal thing that we measure, that's what Cross presented. Look at soluble collagen. I'd expect soluble collagen, based on the shear force, to be highest in the wether, lowest in the ram, and the zero and all treated to be in between. That didn't exactly happen, did it? In fact, the zero and all and the ram were higher in percent soluble collagen than the wether. Well, McCormick in this paper is proposed a hypothesis that it isn't totally soluble collagen, but it's the type of collagen. I told you that type 1 and type 3 collagen were the main collagen, tropocollagen subunits that are found in meat animals. This is one of the first papers that has measured the type 3 percentage. And if you remember, type 3 is smaller, has more disulfide bonds, it's earlier to develop in embryonic development, it's thought to be stronger. So what McCormick's lab is saying here is that if maybe some of the toughness, tenderness differences between rams or animals that are implanted with testosterone-based growth promotants to emulate rams, maybe part of the reason that they're tougher than castrated males, similar castrated males, is not that their collagen is more soluble, but when they start producing testosterone, that they stimulate production of type 3 collagen because it's stronger, and those animals need to more type 3 collagen to be able to do the things they need to do. And indeed, if you look at the values for percent type 3 collagen, the highest percentage was in the rams and the lowest in the wethers, with the zero and all treated animals in between. That certainly follows the relationship seen with shear force more than the percent soluble collagen. So they discussed that in a lot of detail. We've tried to do some of this work as well with type 3 collagen, and notice that of the collagen that was there, about a quarter of it or less, 20% to 25% was type 3 collagen. So it's quite a lot, quite a significant change, and that change may affect shear force. So very interesting. I think that by reading the discussion, not only do you get all the classic research in collagen as a reference for you, but they do a good job of discussing that issue. So please bring your questions to class on Tuesday in regards to these 3 articles, and I hope that you will have a chance to review them as you review this lecture. All right, I'm going to change this a little bit. We're going to end this lecture talking about adipose tissue physiology. And Dr. Smith teaches a whole semester on adipose tissue physiology, so I'm just giving you the basis. And then we're going to talk about adipose tissue when we talk about lipid oxidation, we talk about marbling, and we talk about some other issues associated with adipose tissue. What I really want to concentrate here on is how adipose tissue develops. We know that during prenatal growth, most animals are going to develop some adipose tissue. Most of that adipose tissue is going to be brown, so that when that animal is born, brown adipose tissue, its main job is to produce heat, and for the baby calf or lamb to be able to survive in their environment. And that brown adipose tissue gets replaced with white. This is a picture of white adipose tissue. You can see the individual cells, adipocytes or fat cells right here. You can see that they have a nucleus that's on the exterior. Some of these are small cells. It might be the top of a cell, or it might be an immature cell that's starting to develop. It's hard to tell. But that's basically what adipose cells look like. What adipose cells are derived from mesenchymal cells, embryonic mesenchymal cells that are part of the mesoderm. That's when you have gastralization in the embryo. The mesoderm is the middle cell layer that where muscle cells develop, but also mesenchymal cells. Mesenchymal cells can then differentiate either into fibroblasts, which are going to be the extracellular material for connective tissue, or an adipoblast. The general structure of adipose cells is that they have the ability to fill with lipid droplets. Lipid droplets are hydrophobic, so they're going to eventually coalesce together and try to get away from the water-soluble component of the cytoplasm in the cell. And so they're going to develop these big globules of fat. And one thing that's very interesting is that primitive adipose cells, sometimes it's hard to differentiate an adipose cell and a fibroblast cell, or a adipoblast from a pre-adipoblast, but the most significant component of any adipose cell is that they have the ability to accumulate lipid droplets. So this is the picture from the textbook that shows the mesenchymal cell and how it can either differentiate into a fibroblast or an adipoblast. Notice that the mesenchymal cell has a centrally located nucleus. It's a little bit irregular in shape. The biggest difference between a mesenchymal and a adipoblast is, first of all, notice the real irregular shape. Looks like you took an egg and cracked it on a hot sidewalk and just kind of oozed out there. Still has a centrally located nuclei, but there are these dots. Those dots are lipid droplets. So the mesenchymal cell cannot accumulate lipid droplets, but the adipoblast can. The adipoblast is going to continue to develop, and it will become a pre-adipocyte. The biggest change between an adipoblast and a pre-adipocyte, both of them have the centrally located nucleus. Notice that this is more round in shape and that there are a lot more dots. So this cell has a lot more lipid accumulation, but it hasn't accumulated enough lipid to the point where you start to see a lobe of fat develop. So the pre-adipocyte to developing adipocytes, you notice that the stages are that the lobe develops. That's when it becomes an adipocyte. And then the adipocyte's going to increase in filling and increase in size until a mature adipocyte has a large lobe. Those cells can be up to 100 microns in diameter. During this filling, after the lobe has been developed, the nuclei are going to be pushed to the exterior, and we're going to have the cytoplasm also pushed to the exterior. People who work with fat cells use a Coulter counter and measure the number of adipose cells and the size of the cells that are there, because those are indications of the level of fattening. in postnatal growth, adipose tissue can continue to grow. Muscle fibers do not increase in fiber numbers unless there are some specific conditions where they do, but in general they don't. But adipose cells have the ability to develop in growing and in adult animals. And they are, the size of the cells and the number of cells are more related to nutritional intake than the growth for other cells. One thing that's very interesting about adipose cells, they used to think they were not very metabolically active. Actually, turnover in an adipose cell in the lipids is about 70 days, so there's a lot of metabolic activity. And as I said, the amount of lipids and the size of the cell is very dependent on nutritional state. For example, I've been traveling a lot lately, since August, well actually since June, and so my increase in weight is not due to muscle mass, but due to increase filling of my adipose cells and probably generation of new adipose cells, unfortunately. So postnatal growth is pretty simple. We either have excess energy to deposit as adipose cells or we don't. Now, one thing I want you to understand, though, is that adipose tissue does not develop uniformly through the body. There are actually 5 fat depots that develop, and so in this slide, the first to develop is mesenteric fat. Mesenteric fat is fat around the intestinal tract. It's the first to develop because the digestive system needs support and protection. And so it has a very important physiological function. The next fat, after you have started filling mesenteric and started filling it, then you start filling kidney, pelvic, and heart fat. And that's fat around the vital organs and the reproductive tract. So again, this fat's very important because it provides protection and suspension for vital organs. The third fat to develop will be subcutaneous fat. Subcutaneous fat is the fat that's on the exterior of the animal. I used this picture, I referred to this picture in the background before. This is my dad and my uncle Leland. This was taken when my dad was a senior in high school. And these are 2-year-old polled Hereford bulls that were very well known and champion bulls at the National Western. And they have about 1.5 inches of subcutaneous fat. I can't even think about how much mesenteric and KPH those animals had. So you can tell that they're very fat. If they have a lot of subcutaneous fat, they have fat in the other depots as well. The fourth fat to deposit will be fat between the muscles, or seam fat. We call that intermuscular fat, and that is, we see that heavier, and we have a lot more muscles in the chuck, and we'll see more fat between those muscles. The fifth fat depot to deposit is marbling fat, or intramuscular fat, and that's fat within the muscle itself. I've shown you that picture of the paramecium and those cells. That's marbling. The problem is that marbling is wonderful fat. It's related to flavor and taste. We'll talk about that later. But to get marbling, you have to have some of the other fat. And that's where we sometimes have a balance between not making the animal too fat, but getting them fat enough to have marbling. So the fat depots, you need to know them, and you need to know the order in which they deposit. So in summary, talked about a lot in this lecture. We first talked about basic physiology and structure of connective tissue and its individual protein structure. And then we talked about the physiological changes that occur in connective tissue with aging and that subsequent effect on meat quality. We talked, we had the Cross article, and we had the Purslow article that were important there. And then we also finished that up with the Type 3 article out of Richard McCormick's lab. And then we spent the last few minutes understanding the physiology and structure of adipose tissue, because we'll come back to that. So I hope that this information is informative. Please look this over. Bring your questions to class on Tuesday. We can finish talking about this, and I hope you have a great weekend and beat the hell out of Arkansas. Thank you very much.